Dr. Naidu, who is a system analyst at the Center for Computational Biology and Bioinformatics at JNU.
Basically, a computational chemist. I did my MSc PhD Kanpur. Then I did postdoc in US, UK, and then came back and joined Bose Institute, then moved to JNU in 95. And then onwards, I've been working in JNU initially. Today, I'm going to talk about mainly about structure-based drug designing resources for different drug targets and chemical databases that are available for antimalarial designing and anti-tuberculosis designing. So, all of you know much about traditional drug designing. For the last 15-20 years, a lot of high-throughput screening against different cell-based assays and target-based assays. And they have deposited in the PubChem bioassay and ChemML bioassay, where you got 296 million bioactives for almost 1,500 drug targets, human for around 5,000 human targets, not 1,500, 15,000 drug targets, from 1.5 million SAIDs for different cell-based assays or organism-based assays, from which you got individual active compounds. PubChem gives you active, inactive single assay, where you can do, using those assay compounds, you can do pharmacophore, QSR modeling. Whereas ChemML bioassay gives you only the active compounds for in single assay, and almost around 2.5 to 4 billion bioactives are available for 1.6 SAIDs and 50,398 targets. Some of them are repeated targets, same targets, people have different assays, and they deposit those compounds in the ChemML assay. These are the databases I'm going to use in my work. And they also retrieved a lot of assay compounds from the different research publications and deposit them to ChemML assay. So there are many PubChem-based, zinc-based assays, many chemical compounds libraries are available for virtual screening. And there are many target-based database assays are there. Small molecule libraries are there which you can use for the virtual screening. And for this purpose, we did only a small computer, I7 kind of computer, one can use it and do the high-throughput screening. So there are varieties of assays are there. These are the different drug target databases which one can use. One is a very good database called target database, and the latest one is a Paris at nih.gov, where you got 2,000 targets. Drug targets are listed for 19,683 diseases, 265,000 active compounds. And you can go to disease and find out all the targets that can be related to that disease, or you can find out the active compound and find out what target it binds. Given a target, what kind of compounds are available, whether a validate target or putative target, or what are the compounds that are available for that database. That's a very extensive database, which is still to be developed much further. And what I'm going to use extensively for my work is a TDR database, tropical disease research target database for different tropical diseases like Plasmodium, MTBE, and other organisms. These are the chemical databases which we used extensively in our work for virtual screening, some active databases, particularly PubChem and ChemML. All of you know that almost 5-6 years back, this is a slide where you got 57 million deaths every year, out of that 16 million in cardiovascular disease. Next one is mostly in the infectious disease and parasite disease, almost 15 million percent of the 26% of the deaths. So for all the antibacterials, very few targets are exploited extensively for designing the antibiotics, DNA polymerase, RNA polymerase, and 50S and 30S ribosomes, and IFCPAR and BHPs in the polysynthetic pathway, and cell wall receptors. And very few new compounds are becoming every year as antibacterial compounds. So there are many targets that can be exploited for the antibacterials. So what I've seen in ChemML bioassay, when single organism-based assays like ChemML 364 for Plasmodium falciparum, there are 6,488 SAIDs are there, out of which they found 647,000 bioactive compounds, which are with a different range of activity. Out of that, 338,000 are unique molecules, and some compounds are repeated in different assays. That's why there are number of unique 38,000. So most of the compounds, they don't know the target. they kill the pathogen or inhibit the growth of the pathogen. So we try to make a drug target database for Plasmodium falciparum. Similarly, we did for MTV. Again, there are 1,994 SIDs are there, and 172,000 compounds are assayed, and 89,000 are active unique compounds. So this is the epidemiology of malaria, tuberculosis, and cancer. All of you know, and worldwide in India, incidence mortality rate. So these are the, I won't go into epidemiology of malaria, all of you heard of many times. So these are combination drugs that are being used for most of the drugs, we don't know the target, or either chloroquines or activation even now. Only sulfadoxine and pyrazine drug target is known, and many drugs are being developed now. And these are the from Medicine for Malaria Venture. These are the research and lead optimization compounds, preclinical compounds. This is a few years back, and latest one is this one. One can download it and you can see that how many compounds and translation research, how many are in discovery stage, and then the product development, how many are getting approved, and different stage of approval and combination therapy are being developed. These are the neglect tropical diseases where the different assays have been done for the leishmaniasis, lymphatic filariasis, schimatosis, monosoma. Again, coming back to Plasmodium falciparum, organism-based SCS around 7,098 SCS are there at the moment. Out of that, 115 targets people have found the active compounds, around 14,000 active compounds mapped to the 1,115 drug targets. So those 115 targets are, some of them are repeated. Same target, maybe some assays have been done. So there is redundancy there. And most of the compounds come from initially from the industry, pharma industry, where GSK, Novartis, Broad issued. These are still millions of compounds, identified few thousands of compounds, active compound, different range of activity. And similarly, tuberculosis, around 143 drug targets are listed, around 16,000 actives mapped to the 143 targets. What we are trying to do is taking all the 338,000 unique compounds, we made a drug target and we are prioritizing some targets and trying to map the active compounds which are already tested against the organism, trying to map which compound going to which target. So that will be understand the mode of mechanism, and you can do lead optimization also for the active compound, finding the analogs and screening to the particular target by new molecules. Or pharmacophore or PSO body can put the new compounds. So these are the some of the compounds, Plasmodium falciparum, the target name, how many active compounds are there, how many unique and how many total compounds are there are screened. And these are PPL database which we published in 2014. Around at that time we got 91% targets. At that time we didn't have that much data available in the KMBL. Now the KMBL database every year is lot of active compounds deposited. Another 30-40 targets we identified newly and from the KMBL, and we are putting into the database, putting to the database which may be available. For technical reasons, the data is not available at the moment. We'll try to make it available very quickly. And this is the publication in current drug targets. And this is another International Union Pharmacology database. They made a malaria pharmacology. Most of the active compounds and the anti-malaria drugs and the approved anti-malaria drugs and the anti-malaria drug targets also listed here. And they also do the active compound, defines the pharmacology of each compound, and they try to prioritize the compounds for preclinical and clinical development. This is in collaboration with the British Pharmacology Society. A very good database, and they have used targets also. These antiviral targets and different families of targets are listed here also. And the antivirals also listed, some of them, but not many, as available in the KMBL. So, in collaboration with Professor Sumandar, we screened the Eastern States Transferase GCN5, which Krishna Paul was mentioning it, is very important for global stress of the parasite, and it can remove the artificial resistance if you inhibit the GCN5. So for GCN5, we designed the inhibitors as well as the HDAC1, we designed the inhibitors, screening the active compounds of the plasmodium falciparum and identified the few molecules which bind to this target. And this did the assay on 50% reduction in the paracipapria with 225 nanomolar after 48 hours of incubation. And H3K9 isolation level reduced by 50% at 500 nanomolar. The experiment is done by the Professor Subbarao, Center for Molecular Medicine, JNU. This is the publication in European Journal of Medical Chemistry. Another paper we worked on PFHDAC1. Again, we screened all the active compounds to PFHDAC1, identified few molecules, and also taken some non-active compounds in the KMBL and used them as benchmark and identified the better molecules than the non-benchmark compounds, and did the free energy calculations after doing MD simulation, and we published in the Journal of Molecular Modeling. Then the PFPK already screened large number of molecules in different databases as well as antimalarials to find new molecules. Few molecules we got tested and we had to write the paper after getting the experimental data incorporated. These are some of the molecules which I identified. Delhi DFN is the benchmark compound for the PFPK5. Another target which we use M18 aspartyl aminopeptidase, plasmodium falciparum. And again, we did PSAR pharmacophore modeling as well as virtual screening, identified downline inhibitors, and published BMC structural biology 2016. This is the number of publications, around 15 publications are there, using the anti-malaria screening to different targets and map them and publish papers. And some experimental work with some other is the research work called interested. I did some variability up with him and publish some papers and research work. Coming back to the MTB pluses, anyway, 10 million every year and 2 million people die every year. There are a lot of MDR, XDR, and TDR emerging severe problems for healthcare. So there are no effective drugs for that TB. Again, there is a incidence rate for 1 lakh people, particularly South Africa, Zimbabwe, where HIV is prevalent, and whenever immunity goes down, TB activated, and then two together is deadly, and many people die due to this combination. And these are the exploited drug targets, and these are the known existing drugs for anti-tuberculosis, first line, second line, third line. These are the existing tuberculosis drugs, which are again DNA, RNA polymers, and cell-wall disruptors. And again, the new molecules that have come, beta-quilin, ATP synthase inhibitor, which is approved for multi-drug resistance now. Another two drugs, RV3547, they are approved. Determinate, they are approved. If you go to the new TB drugs, they give you the latest global new drug TB drugs drug pipeline, which are in the lead optimization stage, early stage development, phase 1 to phase 3. And these are the 3 molecules they developed and approved. And they are doing different combination therapies nowadays, regimens, using these 3 molecules along with known molecules already. And around 15-20 regimens have been developed and undergoing clinical trials. So again, we made a MT2 drug target database using some known drug targets from KMBL as well as BED from the literature. We made 170 drug targets and 122 known proteins in PDB or alpha fold structures, and we are trying to incorporate into the database, along with the known active compounds that map to the given targets. For 143 drug targets have known bioactives in KMBL. Some of them are, I told you, repeated. Some claim targets, some repeat assays have been done. And 145 proteins are mapped to PEG pathways in MTB. As I told you, 89,000 unique molecules are there, which we have been trying to screen to individual targets and try to find out the mechanism of action of those active compounds and try to find. You don't have to test it again because they are already on anti-tuberculosis. So if you understand the mechanism, it is better molecules than the known molecules. These are only leads. You can do lead optimization, can find the better molecules. So these are the number of drug targets for which many active compounds are there in the KMBL. This is DNA polymerase 3 alpha subunit, which is essential for mycotuberculosis and which is a target, the validated target. Then we screened this and identified the potential molecules. This is class 1, 115. The other paper in PDA5, acetyl coenzyme, acetyl transferase. But for different purposes, we have to publish quickly. So, thesis of one of the other student. So, we publish quickly in the information. And then we try to design multi-targeting inhibitors, where more enzymes involved in the mycelic acid synthesis, which is part of peptidoglycan synthesis. We try to screen all the antimalarials, anti-tuberculosis molecules, try to find out the molecule which can inhibit many targets. And the Moore enzyme series, and published a couple of papers. These are the compounds which inhibit a class of 3 to 8 enzymes at different level. And again, published paper in the JBST. The other paper in the JBST. Scaffold approach. Published another paper in the Moore enzymes only, finding novel molecules for antimalarial and tuberculosis. This is one enzyme which is cyclopropane mycelic acid synthase, which is expressed very highly in the dormant stage of the MTB. So this target we have screened again antimalarial and antiviral molecules, which is important for survival. It's a latent TB, it will be much better targets. So that's why we use this target. And again,
do we know anything about this enzyme? What it plays a role in dormant TB?
Cyclopropane brings to mycelic acids and this thing reduce synthase. Again, glutamate synthetase of tuberculosis, it is an inhibitors. And these are post-pathogen interaction studies we have done doing system biology approach, identified few targets in the MTB. These are the number of publications which we publish in the MTB. Again, drug target database, we are still uploading it, more data with the gene expression data for all the targets from the TDR database and plasmodb for malaria. These are some of the publications. And again, someone was interested in Helicobacter pylori, and we published 3-4 papers in the Helicobacter pylori. And these are other publications for antibacterial infections and different targets in different organisms. And we studied and designed some inhibitors and published these papers. These are the Prof. is the one who forced me to get into my calcium drug target database creation. Then the MTB we did ourselves, and Sumandar was the collaborator for most of the plasma calcium experimental work. Aparna Dixit helped me in one of the DNA polymerase MTB work, and MS Kumar, who created the PVL database, Amarjit, who worked on the PCN5, other technical people who worked on the database. We got good funding from Center for Excellence in Bioinformatics from DBT for many years, almost 30 years now. And we have got MCIT project around 50 lakhs for a PVL DB database, and a lot of support from DST PAS and EPOE grant for infrastructure, UGC and DST PAS, which is a lot of support for our research work. Recently, we got title project for cancer project for head and neck cancer. Again, we have published around 15 papers related to the head and neck cancer, getting the grant.
Long live India and France friendship.